Welcome to After Hours Engineering. In this episode, we'll set up a simulation that utilizes the Schoko 16-bit SDRAM functionality. For that, we'll need the usual two test bench harnesses and two modules. One, the SDRAM controller, and another emulation of the chip itself. So how do we do this? Let's go. We begin by taking a look at the test harness, at least visually. It starts over here on the left side with the firmware, which is a very tiny little program that does nothing more than just reads and writes from memory. This is a program that's loaded into BRAM. The Femto executes it and talks to the SDRAM controller just as if it was talking to BRAM, and it in turn will then talk to the emulated chip. Now the emulated chip is nothing more than a BRAM that sits there and pretends to be the emulation of the chip itself, and it recognizes only a few of the signals to determine what it's going to do, whether it's going to do a read or a write. Other than that, it's not trying to be a perfect WinBond chip at all. Let's take a side trip first before we get into the harness and take a look at the chip specifications. It all boils down to commands and reading and writing from the chip, which is probably what you expect. The commands are driven by these four pins. And depending on what their combination are, you're activating or telling the chip what you want to do. We'll see most of these being used in the controller itself, but for now we're going to take a look at just the read and the write. So if we come down here to the bank row activation, before you can do a read or write, you have to tell the chip what row and what bank you want to open. And then once you've specified that, you can then call the read or the write. So if we come down here to a read, we can see that the starting column and bank addresses are provided during the read command, not the row, the column. And once you do that, then you're officially in a read operation. And it's exactly the same for the write action. You're going to provide a column and a bank address. So if we scroll down here, you can see here's the write. We're providing a bank and a column, not a row, but bank and column, and then we can write. If we come over here to the read operation and look at its chart, you'll see that it looks similar. We're performing a read, and then we're providing a bank and a column. We've already given it the row during the activate command. So once you've done that, it's followed by a sequence of no-ops. This allows the chip to continue to function without trying to interfere with it. If it sees something other than a no-op while it's inside one of its commands, it'll abruptly quit what it's doing and try to service that command. And a no-op says just keep doing what you're doing. And that's what we want, because we want the RAM to go out and fetch the data and provide it. And in this case, this diagram looks like it's providing a 2-cycle latency. So 2 cycles later, the data starts coming out. And that's what cast latency is. So now we're ready to take a look at the test harness. Now again, this is a ridiculously brief overview of how the chip works. To me, it's more like Spy had a child with SRAM and out popped a SDRAM chip. So take it for what you think. So let's take a look at the test harness. For the test harness, we'll start with the top module first. And as usual, we have a system clock coming in. And again, this is simulation, so there'll be no real I/O lines going into any physical devices. This is the RAM for the Femto. We've seen that before. Nothing has changed. We have the Femto itself, and there's all the signals that we've seen. Nothing has been different. We're simply wiring up our Femto to talk to the SDRAM controller. And now we start to get into some areas that are a little bit gray. This is a new signal for us, and it's detecting when we're interacting with the SDRAM memory range right here, and whether we're initiating an activity, which could be a write strobe or a read strobe. And in this case, we're going to look to see when the signals that are coming in from Femto are all valid at once, which is an activity and the SDRAM is selected. And then we have signals that would typically go out to the hardware, but they'll just go right into the emulation chip. And we have our address for the SDRAM and the read data coming out. And here is the SDRAM controller itself. So we have our control signals that would really go to a chip, but in our case, they're just going to go to an emulation. And these are the signals that we'll interact with for the SDRAM. So we have two sets of signals, one that the Femto is going to interact with and one that the controller is going to interact with on the actual device itself. And then finally we have this extra module here that's going to try to emulate a very minor portion of the SDRAM itself. The intent of the simulation isn't to emulate the SDRAM, it's to exercise the SDRAM controller itself. So this is more of a support and thrown together item. And then the rest of this is just the reset sequence for this stuff. Now let's look at the core of this simulation, which is the SDRAM controller itself. And it's been borrowed from the Zucker project, which is listed down here below. I pulled it out of this project right here. So inside this Zucker project is the code that came from Machdyne that shows how to use their boards. And so I'm adapting their SDRAM for the Femto, which acts a little bit different than the Pico that they used. So we'll start at the top here. We have a bunch of signals that are being calculated, or data that's being calculated. One of them is waiting 100 microseconds. When we look into the specs, we'll see that it requires 100 microseconds for the SDRAM controller to come up and initialize itself and to prepare for the first activity that'll come along. I've thrown in some functions here just for the simulation to properly truncate. I got tired of all the warnings that were inside the controller. I've also adapted this to System Verilog in a very basic way. Here is all the signals that are coming into it, and here's all the signals that would go to the hardware itself. We've seen that before in the top module. And now we're calculating all the periods that we need to wait in between commands and activities that are going on. And when you look in the spec, you'll see that each one, the TRP, TRC, and so forth, each one of these will be in there. And they're usually around 2 to 4 clock cycles on average. And then the system clock, which is running at 50 megahertz, and I believe we'll need a few pills to properly get that frequency. And then we have the command structures that are being built here, and you can see that the mode, when the SDRAM first comes up and after it's initialized, the first thing you need to do is put the SDRAM into a certain mode. And there's several modes. One is individual burst mode, byte access, or word, 2 byte access in this case, half word. Or what we need is a burst of 2 half-word accesses. So this mode will set the SDRAM into a configuration so that every time we read or write to the SDRAM, we'll read 2 consecutive half-words, and that's a burst of 2. That's what these modes are, and if you look in the manual, it'll tell you what each one of these values should be set to. And then the rest of this is just state stuff that helps the state machine move through its steps. Of course, we have our reset, so we give it all a bunch of different reset values, and then we exercise the actual state machine itself here. For every state, next state, we move it into the current state and then evaluate it. Some of these signals I've added on myself in order to help it work with the Femto, and one of these was the initialized. The Femto doesn't know how long it took for the device to initialize, and then I added a variable that tracks that in its active high when it's been initialized. Initiate activity is from us, from the Femto, and then the write mask is from the Femto. So this is all part of the state machine stuff. So the core of it is right here. We go through a reset wait, and then a clock is enabled, and we wait for that. So for each thing that we're doing, we're going into a wait state and waiting for the device to do its thing. You can't just say go into a reset and then immediately go to clock enable. You actually need to wait once you've done a reset. You need to wait once you've enabled the clock. You'll need to wait after you set up the pre-charging situation and the refresh. You'll need to wait for everything you're doing. And this is the large initialization sequence that takes roughly 100 microseconds to take place. And then once that's done, you fall into the idle right here. And so now the SDRAM, while it's idling, it's actually going through restates. It's not just sitting there doing nothing. The controller is continuously issuing refresh commands to it. But as soon as activity comes in, we exit the refreshing loop and head into the actual command that they wanted to do. In this case, it's an activity, and we'll determine what it is. We'll go to a ready wait. So again, we're waiting. We just did an activity, and we're waiting for that. At the end of that activity, we'll determine whether it was a read or a write. And we can tell that by looking at the mask coming in. If any of the bits are turned on in the mask, which is what this shorthanded expression does, it'll determine that it's a write. If none of them are on, then it's got to be a read. The mask only has a bit on, one or more bits on, if it's a write. So let's pretend that it's a read. So it comes down here and it goes into a read. Now in this case, after the wait, it can go straight to a read, and the read will set up for a read, and part of that is setting up for the column which is specified right here. Remember, we needed to specify the column and the branch, or the bank address, and that's what these two lines are doing. We begin our read by setting up the column, or the row, sorry, and the bank address. Once we're done, we wait for that to finish, and then we move on to the reading the lower byte, or the lower half word, out of the chip itself, based on what happens. And by that time, because we waited up here, the data is now available and ready to be moved into the data out portion, the lower 16 bits. Then we go immediately into the head. Now we don't have to wait on this because it's in burst mode, which means the high half word is going to be immediately available on the next clock. So we can move that straight into the upper 16 bits. And then we go into a wait, and with the command being no op. You saw that in the timing diagram on the specs itself. We're using the no op. You have to set this no op. If you don't, the device will see something other than no op and immediately abruptly finish any command, or even abort the command and try to execute the new one. So you definitely need to make sure that you have no ops while the command's processing itself. And the same thing for the write. We're going to issue a row, and then we're going to issue addresses that are part of the column. And once you're done, and you wait for that. So that's the entire thing. So let's take a real quick look at the state diagram that goes along with this state machine. Of course, we start up at the top here onto the assert, and once that's done, the clock is enabled. We wait about 100 microseconds. We fall into the next one, which is going to actually assert the actual clock itself. Then we do a pre-charge all. These are all things that are specified in the manual that needed to be done in a certain order with delays in between each one of them. And eventually we'll get down here to the loading of the mode. And here's the chart for how to determine what it is. We want a programmed burst length. In other words, we want it to be fixed. It's going to start somewhere and then end somewhere versus a single location. A single location would force us to write two separate calls out to the RAM chip just to get one word back instead of two half words. The burst modes allow us to make a very fast two bursts at once, and that's what we specify here in the burst length is 2. It's sequential, of course. We're going to give it an address, and it'll auto increment to the next half word, and then the latency, which we saw was 2, and that happens here inside of this state. Once that's done, we wait, and now we're in idle. And at this point, it's constantly going through and running this refresh cycle right here, going around in circles. And eventually, the valid flag, the Femto will say, hey, all my signals are valid. Go ahead and start figuring out what it is you want to do. We'll wait, and then we'll figure out, well, is it a read or a write? If it's a read, we go down this way. We enable the output. We wait again. You are always waiting in between every one of these states. We'll read, except in the occasion when we're actually doing the burst sequence right here. So it'll come down and read the low word, put it in the low, and then it'll run this state with no wait in between it and put it in the high. Then we'll wait and go back to the idle state. In the meantime, we can, this on the next clock cycle, as we go back to idle, the data becomes ready for the Femto to read. That's a read cycle. And the write is very similar. We're just going to set up the data in the mask. We're going to look at it, and its output will go into memory. Not here. It'll go into memory. Well, we'll do the write of the high. We'll grab it out of there for data in, and we'll wait after that and go back to idle. That's it. This is what it all goes around in circles doing. You can see that A10 in the manual says that if this bit is high, then when we're accessing the row, it'll auto pre-charge and leave the row open and ready for use at another time. And so the row will sit there, the active row will refresh itself, plus the whole entire chip, whatever it can find off cycle. It tries to make the refresh as transparent as possible. All we have to do is go around, and if it's not busy refreshing, then we can go ahead and do a read or a write. And the same thing for the reading here. We're going to look and pull out of the actual address all the data and place it into the top. Again, we don't need to look at the two lower bits because we're word aligned on everything here. So we don't need that. We'll take these bits and put it in here, and the top two, which in our case will be the 8 bit right here. So there's 1, 2, 4. We're at 4,000, sorry. The RAM is at 4,000. We'll put it into there, and then it'll go through the read sequence and come out. So that's the state diagram. The majority of it actually is going through all these states, setting it up. And then once that's done, we enter into a tight loop that's either refreshing or reading or writing from the chip. I wanted to take a moment to look at the original SDRAM controller and what was different from what I did. If you'll notice on mine on the left, I have each one of the states, the refresh 0 for example, and load mode, but each one of those comes with their own wait state here. And on the other side, the exact equivalent would be where you're setting the state to next, but you're changing the return state to something else. In this case, it's going to return back to here. So we set the state to wait, and on the next clock cycle, it goes all the way down and switches to this wait state. And you'll notice as it's counting down, it eventually hits 1, and it transfers the return state into the next state. This effectively is very similar, if you will, to calling a subroutine, but returning back somewhere else. It's more like a go-to subroutine than anything. And I wanted to show how different that was. You'll notice that the code is a bit shorter because we don't have wait states individually for each one of these things. We have one single wait state that knows how to return to wherever it needs to go. In this case, we look at this example, like I said, it'll come to here. This one will actually return to here. So it is, in this case, it's stepping top from bottom, but we may set the return state to one of any kind of things. And I just wanted to point that out versus what I've got over here to the left, where every beginning state has a wait state to go along with it, a beginning state and a wait state, versus jumping all the way back. So you'll see I have no wait state situation down here at the bottom. I just have the default. And that's all I wanted to cover. It's a clever way to use it, and you're more than free to use any kind of style you want. Now let's take a look at the module that emulates the actual chip itself. And by emulate, I mean it does a very few things. Well, the first thing we're going to do is certainly apply all the signals that the SDRAM chip has itself. Here's the command structure, the addresses, the bank, the data itself, the mask, all of these things, the clock enable. If we come down here, you'll notice that all it really is just a bunch of RAM. Now, in synthesis, this would turn out to most likely be block RAM if I finished out the rest of the inference code, but I haven't. I just simply gave it some values to read, and we're not actually going to do a write in this particular simulation. So we take the signals coming in, we concatenate them together to give us that command. So there's those 4 signals that I'd mentioned in the specs. And if we come down here, we'll look at that command to see if it's a read or a write. And if it's a read, we certainly set up the address on the next clock cycle, how many wait states. Now, originally, I had it set to the actual wait states of the controller itself, but it turns out the RAM doesn't abide by those. It actually abides by how quickly. This is the burst mode. So the EMU is actually emulating pretty much just the burst mode, which has no clocks in between it. So I set it to 1. If we come down here to read low, we can see that it immediately times out because it subtracts 1 and comes right in here, takes whatever's in memory based on the address and sets it into the next available value for the data. And we write it out to the command window. And then we transition to read high. And we do the same thing. We grab the next one and we print it out and set the next wait state to 1. And remember, we do need to simulate at least the wait states that are coming out serving for the chip itself. And the same thing for the write. In this case, I'm not writing to RAM because I didn't want to mess with Verilator. Doesn't like you synchronizing updates to any I/O structures. It'll give you an error message saying, I can't remember what it is, but it doesn't like it. And I didn't want to rewrite this code in order to handle I/O inside of a combinatorial block. So I just wanted to cover this real quick. This is the fake RAM chip, and that's it. Now let's circle back to my adaptation of the controller again and take a look at what I was talking about here. The Femto's signals only last for one single clock cycle. And if I come over here to the Femto, one of the signals that we're receiving is the mask during a write. And you can see here that it only lasts during the execution stage. So that's one clock cycle. The problem is that the SDRAM controller may not see that depending on what state it's in. So we need to extend that and capture that. So I added this state right here such that when the valid comes in, meaning there's a write mask there, and we're going to see this in GTK Wave, I'll point it out there too. Then we go ahead and we take that mask and we put it into a capture here. We also capture the strobe that came in for the activity because we need to hold that as well. Again, they only last one clock cycle from the Femto, but it may not last long enough for the SDRAM controller. That's okay. We'll grab a hold of it and hold it so Femto can let go of it and we're fine. So if we take that, we'll come down here and look to see where that's being used. We can see that here is where it's going to be set. So we'll search back up here. We'll look at the mask, and right here is where we're grabbing it. It goes into mask. That's how this state machine works. If I keep going down here. So now we can use that mask. It's been captured and it doesn't disappear after one clock cycle. And we're ready to read it in the ready wait. So we're now at a point where we're ready to run the simulation itself. But before we do that, let's take a look at the firmware that's going to drive the simulation for us. And it's really tiny. It's very small, tiny little assembly here. We set up our SDRAM base so that we can load in T0 with the SDRAM base. It's just to show that the Femto can do stuff in VRAM and the SRAM isn't affected. So I added this just to show that in GTK Wave. We really don't need to do this because we're really testing the SDRAM. But I wanted to show that the Femto, a clear delineation between the Femto touching VRAM and touching the SRAM. So then it comes down here and it grabs out the base of SRAM, which is at 800 here, and loads it into T0. We double dereference it into T1, and now we can go ahead and read. This will cause the read cycle to occur, and we'll see that in GTK Wave. And then I did it twice in a row just so I could see that it clearly separates the two reads out, and then I do a write. And that's all this program does. So now we're ready to actually look at the simulation. Alright, I've started the simulation. And what we're looking at here is certainly a beehive of signals, and I've zoomed out time-wise to take a look at everything. So we're going to take a big overview picture first so that we can see what this thing is all about. Starting at the top, we have the top module, and then we have the Femto processor and what it's doing. We have the SDRAM controller and then the EMU RAM, the emulated chip RAM that we have. So we'll start with the Femto. We expect the Femto to start running things when it's ready as soon as the SDRAM is initialized. So it stays low, and when it's initialized it goes high. And it looks like the Femto is seeing activity. It's beginning to do its thing right about here where it uninitialized. So far things look pretty good. That's excellent. And when it hits the E brake, it finishes. Now I expected this section to run pretty well. We've obviously been using the Femto, so that's all looking good. The SDRAM controller, we know that in that diagram that I showed, the state diagram, that it has 100 microsecond wait. Now in simulation, you might see that it says 1 microsecond here. I've actually just curtailed that. In simulation, we don't need to simulate a reset or an initialization of boot of the chip itself. So I just cut it down to 50 so that it didn't take up forever scrolling all the way over 5,000 clock cycles. But in reality, when this thing is running, it would be 5,000 clock cycles long waiting for it at 50 megahertz for 1 microsecond. So that's good. It looks like it's doing that. And as soon as it's done initializing or powering up, if you will, it goes into its initialization sequence, and that's what all these things are. We'll zoom in a minute to take a look at them, but we're looking at it just from the high level. We have activity here during the instructions. The Femto is executing that little program, and part of it is accessing the VRAM and doing things with it. That looks like that's working there. And then we hit that section of code to make 2 reads and 1 write, and that's what we're seeing. So far it's looking pretty good. And when it does a read, it's going to activate the ready flag so that it's doing its thing. That looks normal. The data that's coming out looks about right. I'll zoom in here to make sure that's correct data, but it does look like it is. If we go back to the EMU RAM, that's the data that's sitting in the first 2 half words and then the next 2 half words. So at a high level, this thing looks like it's doing what it's supposed to. So let's zoom in right here and see what the initialization is. We'll start that on the net right here. Here we are. It's just finished with the initialization over here to the left. And now we're looking at it asserting the clock. So the clock will go high. Sure enough, there it went high right there. We're going through the, zooming in here a little bit. It's going through those init sequences, the pre-charges, the inits, the refresh wait. Let's keep going. It's doing it more. And now it's into that cycle where it's doing, let me zoom out a little bit here, where it's doing an auto refresh. So it's basically the SDRAM is now idling, equivalent of idling, where it's going around in circles, idling and refreshing, and that's what it's supposed to do. We can also see that the Femto has begun executing instructions because the SDRAM has finished initializing. And the only reason we do that is we don't want the code or the Femto accessing the RAM, the SDRAM, if it hasn't initialized. We do know that the BRAM is initialized. It's ready to go right off the bat. And that's what it's doing. It's actually executing instructions up here as it goes along. And these instructions are loading the base address, and of that we're showing that it's executing code out of BRAM, which is fine. And it's eventually going to come along over here and hit one of the instructions that actually is executing the SDRAM chip, which is at 8000000. And that's what we're seeing. And you can see that the valid flag from the Femto came in, went high. We captured it right here so that it waits longer. Fresh. You can see right here we've now exited the auto refresh and went into idle ready wait. And we're now hitting that column read state that was in the diagram. Excellent. You can see that there's that no op after every command, so that we're not, if we had some other command right here, it would really whack things out as the SDRAM tried to execute the command and abort the current one, which is, in this case, would be active, or activity I call it, and the read. So here it is, it's setting up the row on this clock section right here. Then it's going to do a read with the column, and it'll do a read low, and then a read high. Here's the EMU RAM pretending to be the RAM chip, and it pulls out of memory the low byte first, and there it is, and it loads it up and pulls it out into the SDRAM, sees it, and puts it there, and then we read a 0 out. And we know if we looked at the source code, which we'll check out, we make a second read from the SDRAM, and that's where it is. You can see that it came out, did a slight refresh here, and eventually we came and did that. You'll also notice up here that I need to point out is that because the signal went high, the Femto now goes ahead and sits and waits. It's not actually doing anything but sitting here waiting, and it won't fetch and execute the instruction. It has to come out of, in this case I'm not actually loading an instruction, I'm actually loading the T2 register with data, just to show that we can load memory using the sequence. And you can see here, sure enough, it's actually waiting as it's going through, reading the low byte, low half word, then the high half word into it. And when it all has it, it drops its flag, and the Femto recognizes that and it moves right along. This is the typical sequence, and we also know that the code had a write sequence in here, and that's where it's doing it. You'll notice the write sequence is slower, or shorter in duration, because the SDRAM chip has internal buffers that'll grab the 2 bytes and then go on its merry way doing it. And of course, you won't be able to do anything while it's writing. If you try to quickly turn around and read from it, you would find that the SDRAM is busy, our signal would be high. Now here is that section right here is where I wanted to show you why the Femto, if you see right here, the Femto up here is only holding the mask for 1 clock cycle between here and here. That's all. But that we need to hold it longer because the SDRAM controller needs to see it during the idle state, but it disappears right about here. So I added in the ability to capture that into a WR mask, just to give it a different name. And you can see that it holds all the way through the write signal. It only needs to really hold right up here. but I just let it hold all the way to here, and then we clear it out. That was the purpose of that one instruction, those sections of code that I had inside the combinatorial loop that it was doing. So all in all, this chip is actually doing what we expect it to do. It's not perfect in terms of the emulation, but it actually works. Alright, with our new understanding of the Schoko's SDRAM chip and how to interface it to the Femto, we're in a better position to synthesize it. So in the next episode, we're going to attempt to synthesize it on Schoko's SBC. So until next time, peace!